Every rocket we have ever built, every engine, every mission, every $1 billion we aimed at the sky has not come close. Not close to the moon, we've been to the moon. Not close to Mars, we've sent machines there. I mean the stars, those points of light you've been looking at your whole life. The nearest one is 4 light-years away. With the fastest spacecraft we have ever built, traveling continuously without stopping, it would take 6,800 years to arrive. 6,800 years. You could have launched that spacecraft when the first writing systems were invented in ancient Mesopotamia. It would still be flying, and it hasn't even left. Tonight we find out exactly what that distance means, and what it costs a species to want something it will never reach. If you have ever looked at the night sky and felt something you couldn't name, not just wonder, something heavier, something that sat just below the ribs and didn't go away when you went back inside, subscribe. Because what I'm about to tell you won't make the universe feel smaller. It will make what you do here, on this planet, in the time you have, feel more deliberate. Let's begin with something you already know. Distance. You understand distance in your body. You feel it. A kilometer is about 12 minutes of walking at a comfortable pace. You know that, not as a number, but as a sensation. The slight heaviness in your legs. The rhythm of it. The way your mind empties a little when you've been moving for 10 minutes and you're not quite there yet. 5 kilometers to the grocery store. That's a short drive. You could walk it in under an hour. You know what you'd see along the way. 200 kilometers to the next city. That's 2 hours on the highway. You'd want a coffee for that drive. You might listen to the radio, watch the landscape shift. We built our entire understanding of the world on distances like these. Distances tied to effort, to time, to what you see along the way. A distance only becomes real, in the human sense, when you can imagine traveling it. And the reason I'm starting here, with grocery stores and highway drives and distances you've actually covered, is that everything that comes next is going to pull these measurements apart. It's going to leave them behind so completely that by the end of this, a trip from New York to Los Angeles will feel the way a walk across your kitchen feels compared to everything else. But we start here, in the familiar. Because the familiar is what makes the break visible. The distance from Earth to the Moon is 384,000 kilometers. Write it down if you want. It still won't mean anything. Not really. Not in the way that 5 kilometers to the grocery store means something. Here is what might help. The Apollo astronauts traveled at roughly 11 kilometers per second. That is 400 times faster than you have ever driven a car. Not double, not 10 times, 400 times. And at that speed, that almost incomprehensible rocket engine speed that required some of the most advanced engineering in human history to achieve, it still took 3 days. 3 days of traveling through empty space with no landmarks, no rest stops, no horizon to aim for. Just distance, pure distance across pure dark. And this is the moon. The thing you can see craters on with a decent pair of binoculars. The thing that has been lighting your way home on late nights for your entire life. The moon is so close you could, in theory, bounce a laser off its surface and measure the reflection in under 3 seconds. 3 days of rocket travel to reach something 3 seconds away at the speed of light. Close enough to see with the naked eye. Far enough to kill you 40 different ways if anything went wrong. This is the first fracture. The moon is the closest object in our sky. And getting there requires an engineering feat that no other species on this planet has come close to achieving. No other animal has ever left the atmosphere. We did it. We walked on the moon. We brought back rocks, and the nearest star is 100 million times farther away than the moon. 150 million kilometers. Earth to Sun. You cannot visualize that number. Nobody can. The human brain evolved to track the distance to the next water source, the next herd, the next threat. It did not evolve to hold 150 million kilometers in any meaningful way. You can write it down, you can multiply it out. You cannot feel it the way you feel 5 kilometers. Here is what might bridge the gap. The Parker Solar Probe, the fastest spacecraft humans have ever built, capable of reaching 692,000 kilometers per hour when it slingshots close to the Sun, still takes months to complete its orbits. That is not a limitation of the probe. That is the distance, expressed as time, at the fastest speed we have ever achieved. The Sun is our star. It sits at the center of our entire existence, the source of every calorie you've ever eaten, the engine behind every weather system you've ever stood in, the reason liquid water exists on this planet at all. We see it every morning. We know what it looks like. We have nicknames for the feeling of it on your skin in early spring, and we cannot reach it in less than many months. Even if you built the fastest thing we've ever built, pointed it directly at the Sun, and went. The Sun is the most familiar thing in our sky, and it is so far away that the light you see at sunrise left its surface 8 minutes and 20 seconds ago. The Sun you see every morning is the Sun from before you made your coffee. Now, take that distance. Proxima Centauri, the nearest star beyond our Sun, is 266,000 times farther away than that. 4.24 light-years. That is the distance to Proxima Centauri, the nearest star beyond our Sun. A light-year is the distance light travels in 1 year, moving at 299,792 kilometers per second, every second, for 365 days. That comes to 9.46 trillion kilometers. Proxima Centauri is 4.24 times that. With the Parker Solar Probe, our fastest spacecraft, the fastest thing we have ever made, it would take 6,800 years to arrive. 6,800 years. Writing was invented about 5,000 years ago in ancient Mesopotamia. The Epic of Gilgamesh, one of the oldest stories we have, a human being's attempt to understand mortality and what we leave behind, is roughly 4,000 years old. The pyramids at Giza are 4,600 years old. The city of Rome rose and fell, and Rome became Italy, and Italy became modern, all within the last 2,800 years. If we had launched our fastest spacecraft when humans first scratched words into clay tablets, it would still be traveling. It would have centuries to go. Every empire that ever rose and fell, Egypt, Greece, Rome, the Mongols, Spain, Britain, would have risen and fallen while it crossed the dark between here and there, and it still wouldn't have arrived. This is why astronomers needed a new unit of measurement. Not because they like complicated numbers, because kilometers become absurd at these scales. Using kilometers to measure the distance to stars is like measuring the distance from New York to Los Angeles in millimeters. Technically correct, completely useless. So they invented the light year. Not a unit of time, a unit of distance. The distance light travels in 1 year. And they did it because the universe had outgrown the only language we had for talking about how far away things were. The universe didn't ask us if we were ready. It was always this size. We just got here recently and started trying to measure it. 299,792 kilometers per second. Say it again, slowly. 299,792 kilometers. In 1 second. In the time it takes to snap your fingers, about 1/3 of a second, light has circled the Earth twice. Not the concept of light, not the idea of it. Actual photons, actual electromagnetic waves, traveling at the actual maximum speed the universe permits. The fastest commercial jet flies at about 900 kilometers per hour. Light travels 1.2 million times faster than that. The fastest spacecraft we have ever built, the Parker Solar Probe at its peak, travels at about 192 kilometers per second. Light travels 1,560 times faster than that. We do not have an intuitive reference point for this. There is nothing in daily human experience that moves anywhere near this fast. The gap between the fastest thing we have made and the speed of light is not a gap we can close with better engineering. It is not a gap at all. It is a categorical difference. And here is what makes light speed not just a measurement, but a law. Nothing with mass can reach it. Not with current technology, not with future technology, not with any technology that is consistent with the physics of this universe. As you accelerate any object toward the speed of light, its effective mass increases and the energy required to accelerate it further increases without limit. To reach the speed of light would require infinite energy. The universe does not contain infinite energy. Therefore, nothing with mass can reach the speed of light. This is not an engineering problem. It is the architecture of space-time. The speed of light is not the speed limit we haven't broken yet. It is the speed limit that is physically impossible to break, in the same way that it is physically impossible to have a temperature colder than absolute zero. Not a barrier, a definition. Before 1676, the prevailing assumption among scientists and philosophers throughout Europe was that light traveled instantaneously. You opened your eyes and you saw. There was no detectable delay, which meant, logically, there was no delay at all. Even Descartes, one of the great systematic minds of the 17th century, had argued for instantaneous light. The question was considered settled, the way settled questions usually are. Not because anyone had proven it, but because no one had seen any reason to doubt it. Ole Rømer was a Danish astronomer working at the Paris Observatory, and he was not trying to measure the speed of light. He was trying to build a more accurate celestial clock. He had been watching Io, the innermost large moon of Jupiter, disappear behind the planet on a precisely predictable schedule, and he was recording the exact times of these disappearances to create a universal time signal. Ships at sea could use it for navigation. The application was practical, the methodology was meticulous, but the times kept being wrong. Not randomly wrong, wrong in a pattern. When Earth was on the same side of the Sun as Jupiter, the two planets close together in their orbits, Io's disappearances happened slightly ahead of schedule. When Earth had moved to the far side of its orbit, farther from Jupiter, the same disappearances happened late. Over the course of a full orbit, the accumulated discrepancy was about 22 minutes. Every other astronomer who noticed this assumed the problem was in the measurements. Atmospheric distortion, instrument error, the accumulated imprecision of observations taken over months. There was always some error somewhere. The fault was in the data. Rømer looked at the same numbers and assumed the fault was in the assumption. Light was not instantaneous. It had a speed. When Earth was far from Jupiter, the light carrying the image of Io's disappearance had a longer distance to travel, and that journey took more time. The 22-minute discrepancy was not error. It was the transit time of light across the difference in distance. He published his finding in November 1676. The scientific establishment of Europe largely rejected his conclusion. Too unconventional, too much of a departure from the received wisdom. He was wrong, they said, or his measurements were flawed. He died in 1710. He did not live to see his finding verified. 18 years after his death, the English astronomer James Bradley independently confirmed that light has a finite speed, and Rømer's measurement, adjusted for the more accurate knowledge of Earth's orbital size that had accumulated since his time, was found to be essentially correct, and he was the first human being in all of history to measure the speed of the universe's fastest messenger. The first person who understood, not as a theory, but as a measured fact, that information does not travel instantaneously, that there is always a delay between an event and the knowledge of that event, and that delay is real and calculable and unavoidable. He timed the universe, and the universe didn't stop to let him be right about it. Albert Einstein was 26 years old, working his day job reviewing patent applications, when he published 4 papers in a single year that transformed physics. One of them introduced special relativity. Its central claim was not that light is fast, it was that the speed of light is a constant, the same for every observer in the universe, regardless of how fast they are moving. This seems like a small claim. It is not. If you stand still and I throw a ball toward you at 60 miles per hour, you measure the ball moving at 60 miles per hour. If I throw the same ball while running toward you at 10 miles per hour, you measure the ball at 70. Speeds add. This is Newton, and it works perfectly well for everything in ordinary life. But light doesn't work this way. If I shine a flashlight at you while standing still, the light travels at 299,792 kilometers per second. If I shine the same flashlight while moving towards you at half the speed of light, the light still travels at 299,792 kilometers per second. Not faster. The same. Exactly the same. To make this consistent, to make the math not break, something else has to change. And what changes is time. The faster you move, the slower time passes for you relative to a stationary observer. Not your clock, not your perception. Time itself as a physical quantity runs differently depending on how fast you're moving. This is called time dilation. It has been measured directly. GPS satellites orbit Earth fast enough and high enough that their atomic clocks drift from clocks on the ground at a rate predicted exactly by Einstein's equations. Engineers correct for this drift, a difference of about 38 microseconds per day. If they didn't, your navigation would be off by roughly 11 kilometers by the end of the day. Every time a mapping app gives you accurate directions, it is using Einstein's equations about the speed of light. Your phone works because Römer and Einstein were right. The speed of light is not a record. It is the speed below which everything in the universe moves, and above which nothing with mass can exist. It is the rate at which information travels through space-time. It is the rule. Here is the thing that changes once you understand the finite speed of light. Every act of looking is an act of looking backward. When you look at the moon tonight, you are seeing it as it was 1.3 seconds ago. When you look at the sun at sunrise, you are seeing it as it was 8 minutes and 20 seconds ago. The light that enters your eye left the surface of the sun before you got out of bed. When you look at Sirius, the brightest star in the night sky, the one you find by following Orion's belt to the lower left, you are seeing it as it was 8.6 years ago. The light hitting your eye tonight left Sirius during a specific year of your life. Whatever was happening in your life 8.6 years ago. Wherever you were living, whoever you were with, whatever you were worrying about, that light was already on its way. Brief pause. Betelgeuse, the reddish star at Orion's shoulder, the one we opened this film looking at, is about 650 light-years away. The light you see from Betelgeuse tonight left that star in approximately 1375. The Ming dynasty had just been founded in China. Joan of Arc wouldn't be born for another 37 years. Columbus wouldn't sail for another 117 years. Michelangelo hadn't been born. The printing press hadn't been invented. Most of Europe was emerging from the Black Death. And in July 2025, astronomers confirmed that Betelgeuse has a companion star, a younger star orbiting inside its own extended atmosphere, are so close they are predicted to merge within the next 10,000 years. The light we used to make that discovery is centuries old. We are reading a letter that was written before Columbus existed. But here is the part that should stop you. Betelgeuse is a dying star. At some point, astronomically soon, meaning within the next 100,000 years, possibly within the next few hundred, it will explode as a supernova. When it does, it will be briefly visible in daylight. It will be bright enough to read by at midnight. It will be one of the most spectacular events any human being has ever seen. It may have already happened. The explosion may have occurred 200 years ago, or 50 years ago, or last Tuesday. We would not know. The light from that explosion, traveling at 299,792 kilometers per second, or has 650 years to cross before it reaches us. We are watching a ghost and calling it a star. Every telescope is a time machine, not a metaphor, a physical fact. When astronomers look at distant galaxies, they are not observing the universe as it is. They are reading its mail 13 billion years late. On September 5, 1977, NASA launched Voyager 1. It was powered by a plutonium-238 generator. It carried no crew. It had cameras, scientific instruments, and a gold-plated record containing 115 images, greetings in 55 languages, 90 minutes of music, Bach, Beethoven, Chuck Berry, a Peruvian wedding song, the sound of surf and rain, and a mother's first words to her newborn child, and the brainwaves of a woman in love. That last detail is real. Anne Druyan, who would later marry Carl Sagan, sat in a recording session and meditated while electrodes recorded her brainwaves. The recording is on the golden record. If anyone ever finds Voyager 1 and they have the capability to read the record, they will receive, among everything else humanity chose to send into the dark, the electrochemical signature of a human being in love. We sent that into interstellar space. Not because we thought anyone would find it, because we are the kind of species that could not send something into the infinite dark without also sending our best. As of early 2026, Voyager 1 is approximately 25.7 billion kilometers from Earth, the farthest human-made object ever. In November 2026, it will reach a milestone no object we have ever built has reached. One light day from Earth. It will have taken nearly 50 years of continuous travel to cover that distance. One light day. Proxima Centauri is 4.24 light-years away. There are 365 light days in a light year. Proxima Centauri is 1,547 light days from Earth. After half a century of uninterrupted flight, we have covered roughly 1/1500th of the distance to the nearest star. Voyager carries the golden record. It carries our love, our music, the brain waves of a woman in love. It is the bravest and most beautiful thing we have ever made. And by any measure of astronomy, it has barely left the room. Voyager 1 is not a failure. It is the most successful deep space probe in human history. The fact that it is also completely, fundamentally inadequate for reaching the stars is not a statement about our engineering. It is a statement about the universe. April 12, 2016. Stephen Hawking, then 74 years old, communicating through the eye-tracking device that had been his voice for decades, stood on a stage in New York City and announced the most audacious space project in human history. Breakthrough Starshot. The concept, a spacecraft the size and weight of a computer chip, attached to a sail made of reflective material a few atoms thick, accelerated to 20% of the speed of light by an array of Earth-based lasers. At that speed, 60,000 kilometers per second, such a probe could reach Proxima Centauri in approximately 20 years. Add 4 more years for the signal to travel back at light speed, and you could conceivably launch a mission in your 50s and see its first data before you die. $100 million was pledged. Yuri Milner called it humanity's first step to the stars. Hawking, whose entire life had been a confrontation with physical limitation, said simply, "Earth is a wonderful place, but it might not last forever. Sooner or later, we must look to the stars." The physics were sound. The concept was real. The engineering challenges were formidable, but not obviously impossible. The world paid attention. By September 2025, the project was on indefinite hold. Total money actually spent, out of the pledged $100 million, approximately $4.5 million. The laser array that would be needed, the device that would push those tiny spacecraft to 20% of light speed, would require the equivalent power output of roughly 100 nuclear power plants, and all focused into a coherent beam a few kilometers wide, capable of tracking a gram-scale object accelerating at 100 kilometers per second squared. The technology does not exist. The cost to build it is in the tens of billions. The atmospheric turbulence alone, the way Earth's air scatters and distorts any beam that passes through it, represents a set of engineering problems that remained unsolved when the project quietly stopped talking to the press. And even if it worked, even if every problem was solved, every dollar raised, every engineering challenge overcome, the probe would be the size of a computer chip. It would have no ability to decelerate. It would fly through the Proxima Centauri system at 20% of light speed, with perhaps a few hours near the target, taking whatever measurements a chip-sized instrument can take at that speed, and then continue out into the void forever. There is no return. There is no landing. There is certainly no human crew. We announced the conquest of the stars with $100 million and the endorsement of the most famous physicist alive. We spent $4.5 million, ran into the physics, and quietly walked away. This is not a condemnation of the people who tried. The attempt was genuine. Yuri Milner's investment was real. The researchers who worked on the laser array and the sail materials and the guidance systems were brilliant and serious. The universe simply did not yield. Not because they weren't smart enough. Because the universe set the rules before we arrived. Imagine a colony, not a fantasy, a specific scenario. Humans have somehow reached a planet orbiting Proxima Centauri. They've been there for a generation. They have children born on another world. You want to send them a message. You want to know how they are. You compose your message. You transmit it. It travels at the speed of light, the fastest speed in the universe, the absolute maximum permitted by physics. 4 years, 2 months, and approximately 20 days later, your message arrives. If they respond immediately, their answer takes the same time to return. 8 years and 5 months after you sent your message, you receive their reply. You could ask a question, watch a child be born, see that child start school, and receive your answer. You could send your love to someone and be dead before they heard it. Not because of technology, not because of political bureaucracy or funding or the limitations of current hardware, because the space between here and there is so large that even light, the fastest thing in the universe, cannot close it in any human time frame. Diplomatic negotiations between Earth and a Proxima colony. One exchange, 8+ years. A 10-point agenda resolved in real-time dialogue. Impossible. A medical emergency requiring consultation with Earth doctors. The patient would be dead before the advice arrived. Any colony at interstellar distances would not be a colony. It would be a separate civilization. The people there would share our DNA and our history and the language of their grandparents. But they would make their own decisions, develop their own culture, build their own society, because they would have no choice. And the speed of light would enforce their independence with more authority than any declaration. Not A, but B. This isn't a communication problem that better technology will solve. This is the speed of light, expressing the fundamental isolation that the universe imposes on anything that tries to spread itself across light years. And for stars farther than 4 light years, for the Milky Way's 100 billion other stars, most of them hundreds or thousands of light years away, the delay stretches into centuries, into millennia, into timescales that make the question of communication meaningless. There is one clause in the contract, one place where the universe seems, briefly, to bend the rules in our favor. At speeds approaching the speed of light, time slows. Not your clock, time itself as you live it. Your heartbeat, your metabolism, the firing of your neurons, your aging, the rate at which you grow old. All of it slows relative to someone watching you from a stationary position. We know this is true. It is not theory in the sense of being speculative. It has been measured directly. Muons, unstable subatomic particles created when cosmic rays hit the upper atmosphere, should decay long before reaching the ground based on their known half-life. They don't. Time dilation extends their effective lifetime, from the perspective of an observer on Earth, by exactly the factor that Einstein's equations predict. GPS satellites run on the same physics. We correct for time dilation in every GPS calculation, every time you use navigation on your phone. Every time it gives you accurate directions, the universe is confirming Einstein. Also, at 99.9% of light speed, time slows by a factor of roughly 22. At 99.99%, by a factor of about 70. At these speeds, a journey of 10 light-years, which takes 10 years from Earth's perspective, might take you, aboard the ship, less than 2. You could travel to a star 100 light-years away and experience only a few years of the journey. You would not age. You would not be old when you arrived. But 200 years would have passed on Earth. Everyone you knew would be dead. Their children. Their grandchildren. The world that was home when you stepped on the ship would be as remote in time as the world of the American Revolution is to you right now. Your language might have drifted. Your technology would be obsolete. You would return, if you returned, as a stranger. The universe does not forbid the journey. It simply requires that you pay for it in everything that made the journey worth taking. You can go. You just cannot go home. And this assumes we could build such a spacecraft, which we cannot. Not anything close to it. The energy required to accelerate even a small manned vessel to 99% of light speed, the sheer fuel and power and engineering precision, exceeds anything we can produce by many orders of magnitude. Time dilation is real. The ships that would use it are not. The universe offers the consolation with one hand and takes it away with the other. In Orion's shoulder, there is a reddish star that has been watched by human eyes for thousands of years. Every culture that has looked up has had a name for it. The ancient Egyptians watched it. The Mesopotamians charted it. Every generation of every civilization in the northern hemisphere has seen it rise in the autumn sky and known that winter was coming. Betelgeuse, about 650 light-years away. The light you see from it tonight left that star in the year 1375. The Ming dynasty had just been founded. Chaucer was writing the Canterbury Tales. The 100 Years' War was ongoing. That light has been in transit for 650 years, crossing 6.2 quadrillion kilometers of empty space, and tonight it arrives at your eye. In July 2025, astronomers confirmed what had been suspected for years. Betelgeuse has a companion star, a younger star orbiting inside Betelgeuse's extended atmosphere at a distance closer than Jupiter is to our Sun. Astronomers named it Siwaha, Arabic for her bracelet, because it circles Betelgeuse the way a bracelet circles a wrist. The two stars are predicted to merge within the next 10,000 years. An astronomer on the Discovery team said, Betelgeuse and its companion will embrace eternally. And Betelgeuse is dying. Not immediately, not tomorrow, not this century, but on the scale of astronomical time soon. It will explode as a supernova. When it does, it will shine as brightly as the full moon. Visible in daylight, bright enough to read by at midnight. Visible to the naked eye for weeks or months. It is one of the most anticipated events in the astronomical future. It may have already happened. The explosion may have occurred in the year 1800, or 1900, or 2023. We do not know. We cannot know. The light from that explosion, if it has occurred, is traveling toward us at 299,792 kilometers per second, and it will take 650 years from the moment of the explosion to arrive. If Betelgeuse exploded last year, we will not see it until the year 2675. The star you can see with your naked eye, the star that has been rising in the autumn sky for every human being who has ever lived, may already be ash. We are watching a ghost. We are calling a memory a star. Not cruel, not indifferent, just physics. The universe does not announce its events. It lets the light arrive when the light arrives. We read the message whenever we can. And here is the thing about reading messages from the past. Astronomy is not the study of the universe as it is. It is the study of the universe as it was. Every observation, every photograph, every spectrum is a document from the past. The James Webb Space Telescope has photographed galaxies from 280 million years after the Big Bang, confirmed in January 2026. That light has been traveling for 13.5 billion years. We are not seeing the early universe. We are seeing what it was, preserved in light, delivered across a span of time that makes all of human history invisible. We are archaeologists. The entire sky is our dig site, and every artifact we uncover is already gone. In 1950, over lunch at the Los Alamos National Laboratory, Enrico Fermi, one of the architects of the nuclear age, a man not given to whimsy, asked a question that has never been answered satisfactorily. Given the age of the universe, given the number of stars, given that we know planets are common, that we know complex chemistry is common, that we know the building blocks of life appear wherever conditions allow, given all of that, where is everybody? This is called the Fermi paradox. The universe should be teeming with intelligence, and the sky is silent. Many explanations have been proposed. Perhaps life is rarer than we think. Perhaps intelligence is rarer still. Perhaps technological civilizations destroy themselves before they can broadcast for long. Perhaps they're out there, but not broadcasting. Perhaps we're not listening correctly. But the light-speed answer is this. Our radio signals have been leaking into space for roughly 120 years. That means the sphere of space that has received any evidence of our existence has a radius of about 120 light-years. The Milky Way is 100,000 light-years across. We have announced our presence to roughly 0.0001% of our own galaxy. If a civilization exists 1,000 light-years away and begins broadcasting the moment our first signal reaches them, we will receive their response in the year 3024. No one alive today. No institution alive today. A civilization whose language we cannot predict, living in a political reality we cannot imagine, receiving a message from people who have been dead for 1,000 years. The light speed limit doesn't just slow travel, it makes the universe functionally silent at every scale larger than a solar system. Not because no one is speaking, because the messages take longer to arrive than civilizations last. We may not be alone. We may be surrounded, but light-years are walls that physics built before life existed to be lonely behind them. There is a kind of person who, told they cannot have something, decides to stop wanting it. They reframe the desire as a delusion. They call the longing naive. They find a way to be satisfied with what is reachable, and they build a life inside that satisfaction, and they call it wisdom. There is another kind of person who, told they cannot have something, decides that the wanting itself is the point. That the desire is not a mistake to be corrected, that the longing is telling them something true about what they are, not what they can achieve, but what they are made to reach for. The history of our relationship with the stars is the history of the second kind of person. We have always known, at some level, that we could not go. Not really. Not in any time frame that feels human. The distances were always going to be what they are. The physics were always going to impose their rules. Long before we could measure a light year, long before Einstein formalized the speed limit of the universe, people looked at the stars and felt their impossibility and kept looking anyway. Poets wrote about them, sailors navigated by them, children named them, lovers used them as the backdrop for declarations that were really about something else entirely. Not because we thought we'd get there. Because we are the kind of animal that cannot look at something beautiful and infinite without wanting to be near it. That is not a weakness. That is the defining quality of a species that built the Hubble Space Telescope and pointed it at nothing for 10 days and found 10,000 galaxies. The desire is not the failure. The desire is the engine. Ole Rømer sat alone in Copenhagen in 1676 with a table of numbers that everyone else thought were wrong, and he did not capitulate to the consensus. He followed the data where it led. He found the speed of the universe's fastest messenger. He died before anyone believed him. He did it anyway. The team that built the James Webb Space Telescope spent 30 years and $10 billion on an instrument that was over budget and behind schedule and nearly cancelled multiple times. On Christmas Day 2021, it launched. In January 2026, it confirmed the most distant galaxy ever observed. A galaxy from 280 million years after the Big Bang, brighter and more massive and more chemically complex than any model predicted. Telling us that we still don't fully understand how the universe assembled itself. We built a machine to look at the edge of everything, and what it found was that the edge keeps surprising us. You are made of atoms forged in the cores of stars that died before this planet existed. The iron in your blood was created in a stellar explosion. The calcium in your bones was synthesized inside a star that burned for millions of years, collapsed, and scattered its contents across the galaxy as raw material. The carbon that forms every molecule of every cell in your body was assembled in stellar cores and distributed through supernovae before our sun ignited. You are not separate from the cosmos. You are made of it. You are the cosmos, arranged into a shape that can look back at the rest of itself and ask, where did I come from? Where am I going? How big is all of this, and why? No other arrangement of matter we know of can do this. Not the galaxy, not the black hole at its center, not the filaments of dark matter that hold the large-scale structure of the universe together across hundreds of millions of light years. Not the CMB, the oldest light in existence, the thermal echo of the Big Bang itself, filling every cubic centimeter of space around you right now at a temperature just above absolute zero. None of it asks questions. Only you. Only the fragile, improbable, statistically absurd arrangement of atoms that somehow became neurons, that became consciousness, that became a species standing on a pale blue dot 93 million miles from a medium-sized star, looking up at distances it will never cross and asking what they mean. The universe is approximately 93 billion light-years across. You are 2 meters tall, and you are the only part of the 93 billion light-years that knows any of this. That is not a small thing. It is, if anything, the largest thing. We live at a specific moment in cosmic time. The universe is 13.8 billion years old. For the first 380,000 years of its existence, it was too hot for light to travel freely. The primordial plasma was opaque, a fog of unformed matter. When it cooled enough for atoms to form, light was released for the first time. That light still exists. We call it the cosmic microwave background. It has been traveling for 13.8 billion years. It is detectable right now with the right instruments arriving from every direction, and we are erasing it. Not us specifically. Dark energy. The invisible force that makes up 68% of the energy in this universe and is driving the expansion of space to accelerate. In approximately 150 billion years, every galaxy outside our local group will have receded past the cosmological horizon permanently. The cosmic microwave background will have redshifted into wavelengths too long and too weak to detect. The large-scale structure of the cosmos, the vast web of filaments and voids that stretches across hundreds of millions of light-years, will have dissolved. Any intelligence that arises after that will look at the sky and see one galaxy, their own. They will conclude they live in a static, eternal universe alone. They will have no evidence to suggest otherwise. They will never develop cosmology. They will never ask where the universe came from. They will be wrong. They will have no path to knowing it. We have the path. We are standing on it. Right now, in this generation, the cosmic microwave background is detectable. The recession of distant galaxies is measurable. The large-scale structure is mappable. The evidence for the Big Bang is all around us, in every direction, at every wavelength. We built James Webb and confirmed a galaxy from 280 million years after the beginning, and the galaxy looked nothing like we predicted. And we are still here, still looking, still asking what it means. We did not earn this view. We arrived here by coincidence so elaborate that lucky is not sufficient. But we are here, and we are capable of noticing. There are stars in the sky tonight whose light left before you were born. There are stars whose light left before your parents were born, and before their parents, before anyone alive remembers. There is a red giant in Orion's shoulder whose light left in 1375, carrying a message from a star that may no longer exist. And that message arrives at your eye tonight, unchanged, undiminished, indifferent to the 650 years it traveled and to who or what was waiting to receive it. It arrived. Voyager 1 is 25 billion kilometers from Earth. It is moving at 17 kilometers per second. It carries the brainwaves of a woman in love. After 50 years of continuous flight, it has covered 1/1500th of the distance to the nearest star. It is still going. We have never stopped pointing things at the dark and waiting to see what comes back. Not because we expect to conquer the distances, because we are the kind of creature that cannot look at something vast and beautiful and unreachable and simply turn away. The universe is approximately 13.8 billion years old. It will continue for trillions of years more. In the full span of what is and what will be, the window in which anything like us can look up and ask these questions is very small. Smaller than we usually let ourselves feel. Dark energy is patient. It will do what it does. In 150 billion years, the evidence for the Big Bang will be gone. The cosmic web will be invisible. Some future intelligence, if intelligence exists then, will look at a dark sky and believe it has always been this way. But not tonight. Tonight, Andromeda is still 2.54 million light-years away and still visible. The Milky Way still arches overhead. And the CMB still fills all of space at a temperature of 2.7 Kelvin. Betelgeuse still glows in Orion's shoulder, its ancient light still arriving, its secrets still partially unread. The distances are real, the limits are real. We have measured them precisely. We know exactly how far away the things we love are. We know exactly how long it would take to reach them. We know we will not. We are not the ones who will reach the stars. We are the ones who looked up and knew they were there.